This is a review of the material that's going to appear on the Physics 220 final exam of spring 2020. And there'll be 20 questions. It's multiple choice, 4 choices for each question. And 25% of the material will be on material that you've seen since taking exam 3. That's about 5 questions. And everything's been posted so far. We've got a bunch of practice exams up, all homework and quizzes that you've had, except for the bonus homework. The solutions have been posted. My experience is that the hardest thing to recall is scaling, which is a lot like percent change. If something changes by some percentage, 2%, 3%, that's percent change, figuring out how much that affects something else. Scaling is if something doubles, triples, quadruples in size, how will something else be affected? For instance, how will the surface area be affected if the volume increases by a factor of 3? Or if the surface area increases by a factor of 4, how does that affect the linear dimensions of an object, like the diameter of a sphere or the side of a cube? So I'm going to go through the topics that we've had this semester. One of those is scaling, but we did talk about units and conversions, and one of the key things here is making sure you remember how to do area and volumetric conversions. How many cubic meters and a cubic centimeter? Those are often the hardest ones to convert because you have to do either a square or a cube to go from linear to area or volume conversions. Make sure you use the proper number of sig figs. 3 is a good rule of thumb, unless it's an estimation problem, which requires you to use only 1 sig fig if it's an estimation problem. And of course, I just mentioned scaling. How do you get from changing something on some object to how it affects another aspect of that object, whether it's the surface area, the volume, or the length of a dimension of the object. Then we spent a lot of time on kinematics, whether it's the graphical relationship between different things, how is position and velocity related to each other, and acceleration as well. And what I really like about projectile problems is that it really wraps that up nicely. So projectile problems really address the topic of kinematics and put it all together in one really practical problem where you have to look at the free fall problem of how long it takes an object to hit the ground using just the vertical components of the initial velocity. That's what allows you to determine how long it takes to hit the ground. You can take a look at the last couple quizzes which address that. And then once you know how long it takes to hit the ground, if you know the horizontal component of velocity, of the initial launch velocity of the projectile, that doesn't change. So then you can determine where it hits the ground. And you can also determine at what point it's at various heights. So that's a real practical application of the kinematics equations. And so that's typically how I ask kinematics equations on the final exam, is through projectile problems. We also spent a lot of time discussing Newton's laws, forces on a single object, the acceleration that those objects experience as a result of forces acting on them, using the equation F net equals ma, which is an equation we used throughout the entire semester. And F net, of course, represents the entire force acting on an object, the sum of all of the forces. It could be one of many forces. It could be the normal force, it could be friction, and it could be tension, and it could be gravity. Those are the 4 main ones we discussed. And some combination of those results in an acceleration. And what we did later on when we started talking about vectors is we broke that acceleration into its y components and its x components. And that was a good way to actually analyze the forces and the resulting accelerations. We looked at a couple case problems. Looked at the Atwood machine, where you have a pulley and 2 weights, one on either side. We looked at a block on a table pulled over an edge by a hanging block. We looked at the 3-block problem, where you have 1 block pushing 2 other ones, and the interaction forces that occur between them. So those are all possible things that could appear on the final related to forces and applying Newton's laws to blocks. We also talked about the block on a ramp, and we looked at the forces that are associated with a block on a ramp. You have the normal force that's perpendicular to the interface between the block and the ramp. You have the force due to gravity, which is downward, but it has an x component in the direction of the ramp. And we determined what the sizes of those were, where the force along the ramp is going to be equal to the weight times the sine of the angle theta. And from that, we ended up with the equation of acceleration, that the acceleration of an object on the ramp is g times the sine of theta. And of course, if you have friction on the ramp, then that adds another element where you have a friction force acting up in addition to the normal force, and the force due to gravity, which has its x component down the ramp. So the friction is kind of fighting, if you want, or it's in opposite directions as the force due to gravity that's acting down the ramp, and the two act contrary to one another. And so the presence of friction can cause a block to remain stationary on a ramp until it exceeds a certain critical angle. And that critical angle is a function of the coefficient of static friction between the block and the ramp. So what we came up with, if you recall, was the coefficient of static friction is equal to the tangent of that angle. And at that point, that's the threshold, where any object below that angle will not slide, and any object above that critical angle will slide for a given coefficient of static friction. And the multiple block problem is the 3-block problem that we discussed as well. And then you can also figure out the acceleration of an object on the ramp when friction is acting on the object in the ramp. And I gave you an equation for that where a is equal to not just g sine theta, but g sine theta minus mu k times g cos theta. That is the acceleration when you have kinetic friction acting on the block as well as gravity as it's sliding down the ramp. We also talked about vectors. We had the hiker problem, where you have somebody walking in one direction at some distance, and then they change directions and walk another distance in another direction and end up at some final point, and we had to determine what the direction and distance to that final point was from the initial point. So there's plenty of examples of the hiker problems. There's some videos of that. There's quiz problems and homework problems. So take a look at those, because there will be something related to vector addition and the hiker problem on the exam. We also had to apply vectors for the two-dimensional projectile problems in order to obtain the y component of velocity and the x component of velocity. To find those, we had to determine we had to break apart the initial velocity, which is the angle at which an object is fired, into the y and the x components. And so that was something else we did, and that was actually on the last couple quizzes where we did that. We talked about centripetal forces, and we used a number of different examples. Remember, centripetal force is any of the forces we've been discussing: tension, gravity, friction even, and normal force could even be. They could all be centripetal forces that cause an object to continue to move in a circle. And I gave you examples of different cases where this is happening. Anytime you have circular motion, you have some force which is causing that object to move in a circular path. And the equation for centripetal force, or centripetal acceleration, that's the acceleration that an object moving with constant velocity is experiencing as it moves in a circle. That acceleration is the speed of that object squared divided by the radius of that circle. A is equal to v squared over r. And the centripetal force is equal to m times v squared over r. So that is the force that the centripetal force is, you can apply in F equals ma. F could be the centripetal force, and a would be the centripetal acceleration. So you can still apply F net equals ma, even if the object is moving in a circular path, in which case F net will be the centripetal force in that case. We applied it to gravity, and we had an equation for finding the distance an object's orbited from a planet or from the sun. And so we spent quite a bit of time looking at the distance it's orbiting it and the period in which it's orbiting it. And we had an equation that relates the distance and the period and there's the gravitational constant and the mass of the object that it's orbiting. And there's a 4 pi squared in there. So hopefully you can find that equation that addresses orbits, which is a really practical use of Newton's laws. That the fact that it can be applied to orbital problems is very, very relevant. Then after the exam 3, we talked about work, energy, and power. The main thing about work is it has units of joules, and force times distance is how you calculate it. And we talked about conservation of energy associated with work. If you have an object raised to a certain height, you're increasing its potential energy. And then if you drop it, that potential energy of height is converted to kinetic energy of motion. And so that is considered conservation of mechanical energy, where you're converting kinetic energy and potential energy. And energy can also be lost to friction, where you have the force of friction times the distance an object is sliding. That's energy lost. That's energy that becomes heat that had been motion. So it's kinetic energy that gets converted to heat. And we talked about power. Power is the rate of change in energy. And I actually have a little video that compares work, energy, and power. Power is not the same thing as work and energy, but it often gets confused for it. Work and energy have units of joules. Power is units of watts. So that's a very interesting and useful relationship, looking at joules and watts and how they relate to each other. A watt is a joule per second. It's how much the energy of something is increasing or decreasing. It's a rate. Energy is just an amount of something. We then talked about collisions and momentum. We realized that momentum is something that's conserved. The amount of it doesn't change. And if the system is an isolated system, meaning it has no external force acting on it, then the momentum before a collision is going to be, for instance, the same as the momentum after a collision. That's called the conservation of momentum. And when objects collide and stick together, that's called an inelastic collision. Now, momentum is always conserved. We've never seen it not conserved if a system is isolated. And so we can use the conservation of momentum to determine, for instance, how quickly an object's going to be moving after another object collides into it. And I have a bunch of videos that really qualitatively describe that, or conceptually describe collisions, inelastic and elastic collisions. You will not see elastic collisions on the exam, and nor will you see impulse on the final exam, but you will see inelastic collisions, which require conservation of momentum. And finally, we discussed torque and angular momentum. And torque, the most you'll see on torque, this is the most recent material, and I have some videos on this, is, for instance, a seesaw. And you can determine which way the seesaw is going to rotate depending upon which direction the torque is acting, the net torque is acting. You can have torque that's causing it to rotate that way, and you can have a torque that's causing it to rotate that way. And the combination of those two torques is the net torque, and that net torque is what determines the direction the object is going to rotate. Remember, a torque causes an object to want to change its rotation. So if an object's stationary and it experiences a net torque, it'll then start to rotate in one direction or the other. We briefly talked about the moment of inertia, which tells you how easy it is to change the rotation of an object. And finally, angular momentum. I have a video on that, and this is really going to be more conceptual, both torque and angular momentum. I'm not going to put a whole lot of equations in here. It's more conceptual thinking in terms of how to relate them. Angular momentum is always conserved, just like regular momentum is. And we talked about a star shrinking and how its rate of rotation increases significantly as a result of the conservation of angular momentum. I did a couple demonstrations where I was sitting on a stool and spinning and changing my moment of inertia by spreading my arms out with weights on the ends of my arms, my hands. I'm holding weights and bringing it in, and you could see how my angular velocity changed. And that is a result of the conservation of angular momentum. And that really sums up everything we've talked about. For the details, take a look at the videos that are produced and the homeworks and other items that we've discussed throughout the semester. And if you have questions, of course, send me an email. Good luck to you.